Hello and welcome to lecture number 12 in the course Advanced Robotics Applications. In the last class, we looked at robot programming, that is, how would you program an industrial robot using language like VAL2. So in this class, we are looking at, we are starting the study of microcontrollers. That is, when you're controlling a robot using a microcontroller, we will study the fundamentals of microcontroller. How do you program a microcontroller? What is a microcontroller? What is a microprocessor? How do you connect a microcontroller to an actuator? For example, a DC motor, or how do you take sensory input into a microcontroller from sensors like encoders? So we look at first the theoretical aspects, and then we look at basic programming of microcontrollers before we go to the lab and actually implement control systems for robots using microcontrollers. Okay, so this is Introduction to Microcontrollers, where we'll discuss about microcontrollers and microprocessors, but mainly microcontrollers, because in the labs we're going to use microcontrollers for controlling various kinds of robotic devices. Now, if you look at the working of a robot, so this question that first comes up is what is the need for a microcontroller, or what is the need for a controller? So I had explained in the last couple of classes, I'll just very briefly go through it again, that when we have a robot link which has links, and each of the links has a joint, and in the joint we have a motor which is an actuator. Let me say there is a DC motor. At the back of the DC motor there is an encoder, and in the front there is a gear. Okay, and we give voltage to the motor rotates, and because of the rotation of the motor the link moves. Okay, so now suppose I am at this point P1 and I want to go to the point P2. Okay, so here I know what is the coordinates. Let's say it's xy, and here it is x dashed, y dashed. Okay, so at this point P1, what the controller would do is it is going to find out at P1 what is the corresponding angle theta, what is the corresponding angle, say theta 1 and theta 2, numerical values. Okay, theta 1 and theta 2, from inverse kinematics we can find out those angles. Now at the next location here where it has to go, it will again find out at P2 what is the corresponding joint angles, theta 1 and theta 2. Let's call it theta 1 dashed and theta 2 dashed. Okay, so then what the controller does basically is it will do for each of them, there is one controller fixed here. Okay, that's my controller 1, and there's another controller which is fixed there, which is controller number 2. So there's the motor here, encoder, gear. Okay, so the first controller which is fitted here, and the second controller which is fitted there. So what the first controller will do is it will do for angle theta 1, this is controlling angle theta 1, right? So what it will do theta 1 dashed minus theta 1, and find out whatever is the error, or let's call it E1, del E1. This is the error in joint 1. So basically what it means is that this has to move by del E1 there. It has to move by that much angle. Similarly for theta 2, it will do theta 2 dash minus theta 2 and compute this difference E2. That means the joint angle theta 2 has to move by this much, and joint angle theta 1 has to move by that much in terms of motion. Okay. So what the controller would do, it will start giving voltage to the motor. Now once you give voltage to the motor, the joint will start rotating, it will move in that direction. So what is happening is it is coming like this until it comes till there. Okay, so what is the function of the controller here? The controller basically has to find out what is where the present position is and where the robot has to go. Okay, find the difference between them, and then drive the motor such that the difference becomes equal to 0. So if I drive it here and make it 0, and I would make this 0, it means it has reached. Okay, now in terms of a control system diagram, if I draw, then I have we looked at basic control systems, and this is where my controller comes. So this is my controller, this is my robot, this is my robot. Now in the case of a robot, it's basically a motor there. Okay, and here there will be my sensor, for example incremental encoder, and this is my closed loop control system. So this is taken as my closed loop control system. Okay, so what the controller does, what the comparator, so this is my comparator, so this is my comparator here. Okay, so what it does is I know what is the desired, I want to go to desired position theta 1 dashed, and what is my present position? It is theta 1. Okay, so what the comparator does is it finds the difference between them. So this, your theta 1 is coming from here. So what this one is doing, it is doing theta 1 dashed minus theta 1. Okay, and then giving this error, this is my error E1, is giving it to the controller. The controller is amplifying it basically. Okay, Or we can say that this is a number which is being converted to a voltage to the motor, and then it's giving the voltage to the motor as an output. So this is my voltage which is coming to the motor, and the motor is rotating. Okay, so what is the controller doing? The controller is actually amplifying. Okay, it's some kind of an amplifier, it is, we use the term controller, but essentially it is doing some kind of an amplification function to whatever is coming from here. So whatever is my error function there, that is getting multiplied. For example, if I have a Kp and an E, Kp into E, we looked in terms of the P controller. So it has a gain Kp. So that Kp is getting multiplied by the error here, and it is going into the voltage to the motor that side. Okay, this is what I mean by an amplifier here. Okay, so in our linear control systems, we had looked at P control, we had looked at PD control, we had looked at PID control. What these are doing basically is Kp into E plus Kd into E dot. Okay, that's what it is doing. Okay, so this was what the controller was basically doing. So it is amplifying or multiplying whatever is the error and the velocity error there, and then giving it to the motor. Okay, that means how fast the motor is moving or how slow the motor is moving. That will be decided by the controller now. Okay, so that is the need for a controller. And in our case, the controller here in most of our experiments will be a microcontroller. So this is basically an equation. This equation is written in a program. Okay, so this is written in a program, and this program is run or executed in a microcontroller. Okay, so this is my microcontroller there now. So this is how a robot works, and for the working of the robot, we need a microcontroller. Some device that is in which we can embed this, the control loop or the control structure, or we can call it the control law. Let's call this the control law. So the control law will be embedded in the microcontroller, and it is going to execute that. So what we see is that the microcontroller is essentially going to execute the control law, whatever you have implemented in there. It can be a P control, PD control, or PID control. Okay, so what we see is that the microcontroller essentially is going to execute the control law to get your desired objective. Okay, so these are two terms that very often are used interchangeably sometimes, but we should know what is the difference. So first is microcontroller and the other is microprocessor. Now both of this programmable digital processors with necessary peripherals. What this means that these are programmable. That means I'm going to write my control law in the form of a program on this digital processor, okay, and with necessary peripherals. Now what is the meaning of that? It basically means, first of all, that it's programmable digital processor. Okay, it is digital, it is not analog device. Now we are going to put a program in there, so it has to be programmable, and it has to process that program to produce some desired task. Okay, with necessary peripherals. Why necessary peripherals? For example, it may have to take some input. It can take an input sensor, can take some input from some sensor. For example, we talked about encoder. So in the previous case, if you look at this control system diagram here, there's an encode sensor here, which can be an encoder, a position sensor like an encoder which is fitted there. So this information has to go into the microcontroller, that what is the present position, what is the desired position. So there has to be some kind of a peripheral or connection or device through which this sensory input is going to come in. Next, there has to be some output also. Output, why? It is driving a motor. Okay, so here if you see into the previous diagram, the output from here is going to the motor. Okay, so the robot joint has a motor, so it is going to the motor. So there has to be some output which will go to the motor now. Okay, so it requires input, it requires output. It may require other devices, for example, ADCs, analog to digital converters. If there is an analog signal which is coming in, it has to convert to digital. Okay, so microcontrollers and microprocessors are essentially programmable digital devices, or it's a programmable digital processor with necessary peripherals. Okay, you may have data storage, you can have CPU. Okay, so these are the various peripherals that may be required. Now, what is the function, or what do they do? So these are essentially sequential digital circuits that perform the task by executing a program or a set of instructions. Okay, so we are going to focus on robot control. So we understand that a microcontroller or microprocessor is a digital device. It is not an analog device. Okay, so if there is an analog signal coming, it has to be converted to digital first. Okay, so first it's a digital device. Second, it performs the task by executing a program. So there has to be a program. You have to write a program. What will the program do? It could be your control law. Okay, so the control law that we are going to implement your Kp into E plus Kd into E dot, that's your control law. And this is the program which is implementing it now. Okay, so I hope you're making the connections between what I'm saying. So it's a digital circuit that performs a task. What is the task in our case? To move the motor by executing a program or a set of instructions. Okay, so this is a very general definition. Our focus is only on robotics, so I'm taking the focus only on robotics now. So it's a digital circuit that performs a task by executing a program or a set of instructions. Okay. Now, if you look at the difference, then what is the difference between these two? So in terms of definition, both microcontroller and microprocessor are the same. They are digital devices. They are sequential digital circuits that perform tasks by executing a program. Both of them are the same. There's no difference. So what is the difference between a microcontroller and microprocessor? Now, a microprocessor essentially is a general purpose device, like your PC or computer or laptop. So a microprocessor is a general purpose device normally, and it has an external memory for program data and instruction execution, and requires data movement from the storage. Now this is mainly used for computation and is a general purpose machine for general purpose applications. For example, when you're using your PC, you can use a PC to control a robot. Yes, you can do that. But you can also use your PC just for computing. You can connect your PC to your camera, for example. Okay, so you can do input-output with your PC also. Okay, but it's a general purpose device. Okay, and in the PC there is an external memory in which we store the program, and the data is stored on the external memory now. Okay, so a microprocessor basically is a general purpose device with an external memory on which the program and the data is stored. So when the program is to be executed, it can be pulled from the memory. The data can be pulled from the memory and stored back into the memory. Okay, and it's a general purpose device, and hence it is more expensive, like your PC or laptop. Now a microcontroller has an on-chip memory and associated peripherals. So in one chip, it has an on-chip memory on which the data can also be stored. Okay, and it consists of a memory, a processor, as well as input-output interfaces. So microcontrollers are programmed to run a certain task. If there is a need to change or enhance its functionality, one must install a new program on the chip. So a microcontroller is essentially a single chip device which has an onboard memory. Okay, unlike a PC which has an external memory. Okay, so that is the fundamental difference between a microprocessor and a microcontroller. The microcontroller may have input-output interfaces also, like ADCs, DSCs, which it can do. Okay, but the basic difference being the on-chip memory and the external storage. That's the fundamental difference. Now, obviously, if it is a one-chip device with an on-chip memory, the memory will be very small. Okay, and it is not a general-purpose device. Okay, so it may not be able to do all kinds of other things. For example, in a PC, you can connect a monitor, you can connect a keyboard, you can do all kinds of things. Now, in a microcontroller, these microcontrollers are basically task specific. So it has an onboard memory and is task specific, and this can be found, and these are used in almost all appliances today, right? Household applications, electronic applications, industrial applications, robotic applications, you name it, there'll be a microcontroller somewhere. Okay, for example, even in household applications like microwave ovens, TV sets, toys, okay, then cars, or automobiles. So microcontrollers are used mainly because they are easy to program and have a wide range of functionalities, but they are not general purpose. So once you put the program onto that, a single chip microcontroller, it will be doing just that. It is not a general purpose machine which can do a lot of other things. Okay, so because of which the cost is low. So the cost would be, this would be very, very cheap. Now how cheap is cheap? Okay, so a microcontroller will cost you about 500 rupees, that cheap. Okay, whereas a PC based general purpose microprocessor will be much, much more expensive. Okay, so now let's look at the difference between microprocessor and microcontroller. Now a microprocessor, okay, something like a PC or a laptop. This is the block diagram which is showing the microprocessor, the block diagram. So you have a CPU, the central processing unit, which does the computation. There are registers, ALU, arithmetic logic unit, okay, and it has this address bus. There are different buses which which connects to the external memory. So the program and the data may be stored on the, will be stored on the external bus. Okay, now let's look at the difference between the microprocessor and a microcontroller. Now this block diagram shows the microprocessor. Now in the microprocessor, what we see is that there is a CPU, the central processing unit. There is an arithmetic logic unit, which is the ALU. There are registers in which the computation is done, and then the data is pulled from the register, or it can be stored on the register. And there is an external memory. So this external memory is the one on which we store the program and which we keep the data. Okay. So when the program has to be run, it has to be fetched from the external memory, and it can be whatever data is generated can be put back into the external memory. Okay. So these are the address buses by which the connections are made to the external memories and things. Okay. So this is essentially a microprocessor, something similar to our PC. Now, if you look correspondingly the microcontroller, okay, what we see is that this is a single chip device. So this is one chip which has the CPU, it has the RAM, the ROM, that means the memory is there on board. Then there are input-output ports, and there are also COM ports. Okay, serial COM ports are the input-output port is there, and timers are there. And it also has connections like the data bus, control bus, and the address bus. But essentially, it is a single chip device. So this is a single chip device, and hence it is much smaller. Of course, the limitations are there. So it doesn't have a very large memory. It is not very fast. You cannot connect a lot of other things onto that. Okay, but it is very cheap, and it can do a dedicated task very easily. Okay, for example, if you're controlling the temperature on your AC. Okay, so if you're controlling the temperature of a room AC, then you just need to control the temperature. Okay, you don't need to measure, for example, humidity, or you don't need to control a motor, and you don't need to do all kinds of other things. Okay, so also when you're controlling the AC, you may not need a display, you may not need a keyboard, you may not need all of that. Okay, so if you're controlling the AC temperature, so we just we set the temperature. Say, for example, you want to set the temperature to 24 degrees C, and suppose the temperature of the room is 30 degrees C. So what the microcontroller does, essentially, it will take the difference between these two. That minus that is 6 degrees C. Multiply with that some gain, okay, and then drive the AC. Okay, put it on or put it off. Okay, so the moment this becomes equal to 0, that means these two temperatures become same, it will switch it off. Okay, so there's a very simple control program or a control algorithm which runs an AC. It simply checks the desired temperature minus the present temperature, takes the difference, puts it in the control law, and then does whatever it has to do. Either switches on the AC or switches off the cooling of the AC. Okay. Now, only for doing this, a single chip microcontroller is enough. You don't need to put a PC to do that. A PC can also do that. Okay, but if you put a PC onto that, the cost immediately goes up. It becomes more complicated. Whereas a single chip microcontroller is a single chip which can be put in the AC. Okay, so I hope it is clear what is the difference between a microcontroller and a microprocessor. Now this table also gives us the difference. So in terms, this is a microprocessor, this is a microcontroller. So if you see in terms of function, a microprocessor generally processes general tasks. For example, you can do data processing. Microprocessor, so computation can be done, data processing can be done, computation can be done. Okay. Whereas in a microcontroller, both process and control specific tasks. So you can only take care of process and control of very specific tasks. What kind of specific tasks? For example, controlling the temperature in a room, or controlling the speed in a washing machine, or by putting on your TV. Okay, so those are very specific tasks. Okay, they are not general purpose tasks. Whereas running a computer program to generate data or to execute something is a general purpose task. In terms of memory, there is no inbuilt memory in a microprocessor. It just has to connect to an external memory. Whereas in the microcontroller, we have an inbuilt ROM and a RAM. So the memories are on the chip itself, as seen in this figure here. Now, in terms of application, this is a more general purpose machine. For example, a PC, a modem, a printer, these are all general purpose machines. Whereas this is a very specific purpose. For example, AC, washing machine, home automation. Home automation means switch on, switch off light. Okay, that is home automation. So that a microcontroller can do. Complexity, these are more complex, larger number of instructions. These are less complex because it's only one chip. Cost, these are high in cost, so design time is more. A microcontroller is very low in cost. For example, it can be only 500 rupees for a microcontroller. Okay. Efficiency is less, and this is more. Why? Because here the PC has to do a lot of other functions. It is running the OS, it is running input output, it is having a keyboard, it is having a display, and so many other tasks could be running on the PC simultaneously. Whereas the microcontroller is just running one task. So in that sense, it's more efficient. Now, in terms of architecture, this is just theoretical. There are two architectures that are used. Microprocessors with von Neumann architecture. This is also called the Princeton architecture. This is also called the Princeton architecture, and the other is the Harvard architecture. Okay, there are two architectures. Now, in the von Neumann architecture, the program and the data are stored in the same memory. In the Harvard architecture, the program and data are stored in different memories. Okay, so this is stored separately, this is stored together. So there is only one line, and here there are two. Some example, 8085, 8086 are microprocessors, very early microprocessors. Microcontrollers, 8051. Okay, these are very, very old. We don't use them today anymore. But this is just to give you an example of what are the microprocessors and microcontrollers that were originally built many, many years ago. Okay, let's move on now. Different types of microcontrollers. So we'll be focusing on microcontrollers. Okay, because we just want to control a joint. How do we control a joint? By giving a voltage to the motor and getting input from the sensors. Okay, that is what we'll do, and that is good enough to be done by a microcontroller. Now, it can also be done by a PC, but why make it so complicated? So if you can do it with a microcontroller, it's much cheaper and it's very easy. Okay. Now, microcontrollers can be 8-bit microcontrollers. They operate on 8-bit data applications, very simple applications, for example, basic control applications. So Atmega 328, the one that we'll be using, is one such example, which is an 8-bit microcontroller. There are other microcontrollers, for example, PIC16 is also an 8-bit microcontroller. Okay, you can have 16-bit microcontrollers. This operates on 16-bit data. Applications are a little bit more for more complex applications, for example, portable devices, low power switching on, switching off a light. Okay. Then we have 32-bit microcontroller architecture. They operate on 32-bit data. So essentially, this is the simplest, okay, because it operates only on 8-bit data. This is 16, little bit more complex. This is more complex. And nowadays, you can also have 64-bit. Okay. So as you become, as the data size increases, it can handle more amount of data. It can execute better programs. Okay. But the cost, of course, goes up automatically. Now, a microcontroller is to be used. Okay, so this is something like a microcontroller. So when we said, I use this word microcontroller, so this is the microcontroller, this one. Okay, now to use a microcontroller, which is a single board chip. Okay, so this is my microcontroller. It's a single chip. Okay, now the single chip, you need to connect it to various devices. Okay, to perform a task. For example, if it is taking a sensory input. Okay, if it's giving an output to the motor, okay, if there is a connection to a ADC, okay. So to make those connections, so this is we need to integrate all of them. For example, we need to integrate sensors. Okay, so we need to integrate sensors. We need to take output to give output to actuators. It needs a power source. Okay, so we need a power interface. Okay. And then there can be some controller hardware and software issues. There is some signal conditioning. For example, it has ADCs, it has filters. Okay. Now, all of this together will make this microcontroller useful because it has to interface with the real world. Okay. So, interface with the real world. Okay. Because of which we need to have other kind of interfaces by which you can interface with the microcontroller. So now for that purpose, basically what several companies have done is they have made something like a developmental board. So you might be familiar with developmental board like this, like the one shown here. Okay, so you can connect various pins in here for a diode or a triode, make connections, give power. So this is a developmental board. So similarly here, this is a development board in which you have the microcontroller which is here, and the peripherals are fitted onto that and are on that board itself. So a printed circuit board designed to facilitate work with a particular microcontroller is what is shown here. And the typical components that are there here, there is a power circuit, there is a programming interface. How are you going to program this? Okay, so there is a programming interface. There can be display interfaces. Okay, there can be there are basic inputs. There can be buttons. Okay, you can switch on, switch off. Okay, you can reset. There can be LEDs. There can be input output pins by which sensory input can be taken in, sensory output can be given out. Okay, so this is similar to our development board, and this is what is shown in the next slide, this one here now. So in this development board, what you can see is there are pins and there are pin numbers. These are what we call as pins. Okay, and pin numbers. Okay, now these pins have pin numbers, so you can see 1, 2, 3, 4, 5, 6 like that. Okay, so if you connect a wire into pin number 1, then automatically you know that whatever is the function of the pin number 1, it will be doing that function only. Okay, for example, it's in pin, it's an analog in pin, so it will take, and you connect an analog sensor there, so it is going to take an analog signal in that pin. Okay, now this is basically what we call by developmental board, and different companies make them. The one we'll be using is the Arduino Uno microcontroller. Okay, board, basically it's called the Arduino Uno, and the microcontroller is sitting here. These are all pins. I'll explain the meaning of the pins. They are basically channels or pins. Okay, and whenever we connect something, we'll connect it to these pins like this. Okay, so when I'm connecting a sensor, I'll be connecting it on that pin. When I'm trying to control a motor, I'll connect it to some other pin. If I want to take a 5-volt signal, I can take a 5-volt signal from here. It says 5 volt, so that can generate 5 volts. If I want to connect to a ground, I connect it here. That says ground. Okay, so there can be analog pins, there can be digital pins, there can be PWM pins. Okay, this is where we interface with the computer. Okay, and this is my set and reset button there. Okay, now this is the microcontroller called the Arduino, which I'm going to use for most of our experiments. This is good enough for our job. Now, what is Arduino? The word Arduino essentially means these three things. It's a piece of physical hardware. So this is the piece of physical hardware that I just showed. It contains the microcontroller pin in there. It has input output. It has power in. There is communication with the PC. Now it also has a programming environment. Okay, so it is a programming environment which is there. Okay, which we'll come to shortly. So what we can do is we can run we can write the program in the PC in the programming environment, and then we can transfer it onto the microcontroller. Once we put it on the microcontroller, it will start running. Okay. Now there is also a community or a philosophy on the internet. Okay. So a lot of people use this microcontroller, and they sometimes discuss their projects online. Okay. So you can go online and on the internet and check in terms of this microcontroller, Arduino microcontroller. There are different microcontrollers and different communities are there. So for the Arduino microcontroller, you can check what is the various discussions, various projects, various problems. If somebody finds a bug on something, they will report it. Okay, that is, so there is also a common philosophy of using, or a general, should we say, a community of Arduino users online. Okay, so all of these three things are there. One is the hardware. The second is the program, on which you write the program and download it onto the Arduino. Okay, and third is there is a community of all users who are online and they keep discussing. Okay, so another very important thing is Arduino is an open source hardware which consists of an Atmel microcontroller. So what is this microcontroller sitting in there? It's an Atmel microcontroller, and it's a programmable digital board that is easy to use software with an IDE. So which IDE basically means an integrated development environment that runs on your computer. So your IDE, integrated development environment, which is a software basically in the form of a GUI, as you can see here. Okay, this will run on your laptop. You write your program there and then download it onto the Arduino board. Okay, and the microcontroller is an Atmel microcontroller here. Okay, now we are using the Arduino Uno board, so you can see the name here, Arduino Uno. Okay, now this Arduino Uno 328 is the microcontroller. It's an 8-bit processor. It is an 8-bit microcontroller. It has a USB interface. You can look at this here. This is my USB connector. So this side of it will go into the microcontroller, and the other end is a USB-A USB connector, which will go onto your PC. So this will connect to your PC. Okay, so you can connect your microcontroller to the PC by using this wire or this connector. Okay, and in terms of specifications, it is operating at 16 megahertz, which is a very slow speed actually. Computers speeds are in gigahertz. This one is in megahertz. Okay, because it is small, it has a very small memory. It is 8-bit, but that is enough to do very simple tasks. Okay, it has only 32K memory. It has 6-channel 10-bit ADs. It has PWM. Okay, and we'll come to this as we go along. And the power is in the standard board design, and it is very, very user-friendly kind of. Okay, so it's an open source hardware. That's the most important part, or the most interesting part, is that this is an open source hardware. So all the programs are available. They are open source and they are available online. Okay, so you can buy this also from Amazon. This board is available in Amazon. You can buy it from any shop, and it costs only about 500-600 rupees. And it's surprisingly very good, even for very simple robot control. That is something we'll be seeing. Okay, so this is how you connect. Now, these are just for information. There are different types of hardwares. Okay, so you can have Arduino Uno, you can have Nano, you can have FIO, you can have Mini. These are different names of microcontrollers. Okay, and basically this is showing you that what is the basic difference between them. Let's not worry too much about them, but this is just to tell you that these are so many kinds of microcontrollers which are there today. Okay, say for example, digital input, digital output, analog input. Okay, what is the difference? You see, it is here it is 0 to 5 pins. Okay, it is 0 to 7. It has more. PWM pin numbers are 3, 5, 7, 9. Here it is 3, 5, almost same. Okay, so there can be some differences, but they would normally be minor. Okay, so we'll be focusing on the Uno microcontroller. In terms of the AVR chip architecture and a simplified version, let's not go too much into details, but if you're interested that inside the chip, what is the architecture, then this is the one that actually shows the chip architecture. Okay, so fundamentally there is a CPU which does the computation. Then there is a ALU, arithmetic logic unit, which actually does the addition subtraction. Okay, taking instructions, taking data from the RAM, and then after it finishes, it puts it onto the registers. Okay, and you can also interface it with analog comparators, AD converters, LEDs, then all these other input-output ports are there, interrupts are there, watchdog timers are there. Okay, so essentially it is something like this. Okay, so you have a CPU, then there is a RAM and an EEPROM, then there are timers, and there is an interrupt program. If something goes wrong, you can interrupt it. There's interrupt external switch also. Then there are ports by which you can connect, or pins by which you can connect, and other peripherals which can be connected onto. So the program is on the ROM, okay, and it is and it can run onto the. Once it runs, it comes onto the CPU and it takes the data to and from the RAM and the EEPROMs. Okay, so this is the full chip design. This chip is same as this one. Okay, that is the inside of the chip, what the chip looks like inside. That means what this looks like inside. Okay, what is that inside? We are not getting into too much of details. That is not our point. Again, the Atmega 328 internal architecture has the pins here. You can see these are pins. Now, which of those pins are doing what is written here? For example, this is a ground pin. Okay, then which pin is doing what is written here? Let's not get too much worried. Let's not worry too much about that. Okay, this is we are simply going to use it as a user, not as a designer of microcontrollers. Okay, basic features of the Uno. The operating voltage is 5 volts and the input voltage is 7 to 12 volts. And it has digital input-output pins, 14 of which 6 of which provide PWM signals. You have 6 input pins. Now, it can give a DC current per pin out of 40 milliamperes. Okay. Now, we talked about, sometime back, I talked about the control law as being a gain, basically being an amplifier. So, the control law, okay, was working as a gain, or was working with gains, and can act as an amplifier. Now the current that it can go out is only about 40 milliamperes. Now this may not be enough to drive large motors. So this cannot drive large motors. That may require up to 5 amperes or maybe as high as 15 ampere current. So it can't drive that. So you need an amplifier or a power supply from outside. Okay, so that will come in here. So that's your external power. Okay, that is basically required for amplifying whatever signal is coming from the microcontroller, and then it's going into the then it's going to drive the motor. It has a flash memory of 16 KB. It has SRAM and EEPROM of 1 KB and 512 bits, and it has a clock speed of 16 megahertz. Now this speed is not very fast, it is very slow. If you compare with the PC speed, the speed of PCs would be somewhere around 3.5 or higher gigahertz. Okay. So in that sense, this is very, very slow. Okay. But is enough to run processors that we want. Why? Because the PC will be doing a lot of other things at the same time. Okay. So PC could have a high speed, but it could also be doing lots of other things. Okay. Whereas this one has a very simple program which it will run, and the simple program will do the single simple task. Okay. Now this is what the Arduino software looks like. So the Arduino IDE 2.3.2, this is the one we'll be using in the experiments. So if you are planning to do it yourself, okay. So the Arduino IDE is 2.3.2. You can download this free. You can download free from internet. It's an open source software, so it's freely available. You can just download it and install it onto your PC. Only be careful, the version is Arduino IDE 2.3.2. Okay, and you can complete your Arduino setup. What does each of the program look like? It looks something like this. I'll come to this in more detail as we go along. Okay. So after you download this onto the PC or laptop, okay, then we have to set it up. Okay, so when we set up the, you can look at the IDE, the GUI, what it looks like. Okay, so here there are tools. In the tools, there is the board that you're using. So the way we are progressing, let me just explain. Let me explain and then come back here. So first is you download the Arduino IDE 2.3.2, then connect the Arduino with the USB cable with the PC or the laptop. Okay, I had shown it some time back. Okay, so you make the connection between the board that you have. So this is the board. So this is the cable or the connector. Okay. So with this one end of it goes in here, the other end goes into your PC or laptop. You make the connection, okay, and connect it to your board. Now this board can be Arduino Uno, it can be Uno, it can be Fio, it can be something else. Okay. So the computer doesn't know which board you have which board you have connected. So the first thing that we need to do is we need to configure the board. Okay. So how do we do that is here. So connect the Arduino with the USB cable with the PC, open the Arduino IDE software, select the board type as Arduino Uno, that's the one we'll be using. Okay, or if you're using some other board, you can choose the board. Okay, that is being shown here. So if I go to tools and I go to board and it goes to the Arduino, the board manager, here it goes there, it shows, see how many of these Arduino types are there. So you have Arduino Nano, you have Arduino Micro, you have Arduino Mini, and you have whatnot. Okay, so we are going to use the Arduino Uno. So we have to choose this one. So the laptop now knows, or the PC now knows that the hardware you have connected is an Arduino Uno. Okay. The next, you need to set which port of the PC that you have attached your Arduino to. Okay. So when you're inserting the USB onto your laptop, you must also know that which port of the laptop has been accessed by the Arduino software, or by the Arduino board, sorry. So for that, you go to the tools again. In tools, you go to port, and it will show you how many serial ports are there. It could be COM1, COM2, COM3. Okay, it can be COM1, it can be COM2. So wherever it is connected, it will show you that one. So you have to choose that one, and it will show you that this is connected to Arduino board on COM3. In this particular case, it's COM3. So the Arduino board will show you that it is connected to COM3 now. Okay, so you just click on COM3. Now the PC understands that the board is connected to COM3 of the PC. Okay. Now in order to upload a program, the program that is suppose for example this is the program. Okay. Now I need to upload the program onto the microcontroller. So this program is on your laptop or PC. So this laptop, from the laptop or the PC, it has to be downloaded onto the, so what we can do, we can use here and say upload. So what it does is it will upload the program onto the microcontrollers. Okay, so you write the program in your laptop. We'll see all of this as we go along, as we progress in the lab classes, and then you can just upload it. Okay. So if you say upload, it will simply say it will upload to the microcontroller. You can also compile and see if there's an error in your program. So if you compile the program and there's an error, then it will show an error. Okay. Or you can upload straight. Now if you upload, it will compile first and then it will upload. Okay, so it will compile and the program and then it will upload only. If you simply say upload. If you say compile, it will only compile. Okay. So this is how we connect the Arduino Uno software. First, you connect the Arduino with the cable to your PC or laptop. Then open the IDE software which you have downloaded. Then configure which board type you're using and choose Arduino Uno from the tools option. Then select the port type and it will show that the Arduino Uno is connected to which COM port of your machine. Okay. For different machines, it will be connected to different COM ports. Different laptops have different configurations. Okay, so whichever one it is connected to, you can choose that one. Okay. Next is you can verify, compile from the sketch menu to compile and the code such that there is no errors. Then you can upload onto the board. The moment you upload it onto the board, it will start working. The program will start running. Okay, and whatever you want it to do, it will do. Okay, now let's come and see a little bit more. This is a pin diagram of the Arduino Uno. So you can see that the pins are color coded. Now one pin can do more than one thing. Okay, for example, here you can see this is the ground pin, means 0 volt. This is ground. This is the 5 volt. This is 3.3 volt. That means if I collect a pin here, okay, if I connect a pin onto here, should I say, if I connect a wire onto that, I can take 3.3 volts. So it provides 3.3 volts. If I connect here, I can get 5 volts. Okay. If I connect it here, then it gets grounded. Okay. Now this part is going to your PC or laptop. Okay. Now these are the other pins which are called analog in pins. It's written here. You can see it is written here as ground power pins. Here it is written analog in pins. So A0, A1, A2, A3. So these are analog in pins. Okay. So it is written here in terms of analog. Now they can also be set as digital pin. So the color coding is different. So you need to set it, okay, as an analog pin or a digital pin. Now in this case, here again, you see on the right hand side, there is 0, 1, 2, 3, 4. These are all there. And these are the AVR pins. Then there also, these are digital pins. Okay, so it is coming as digital here. Okay. And right here, if you note very carefully there, it is saying PWM pin. So it says PWM and there is this tilde sign. So whichever pin has this tilde sign, that is a PWM pin. What is PWM? It's a pulse width modulation. So for driving motors, especially the servo motors, we are going to use pulse width modulation. Okay, I'll just come to what that means. So if you're connecting it to the 3, 5 or 6 or 9, it basically understands that this is a PWM pin. Okay, and you're trying to drive a motor on the other side. Then there are interrupt pins. So this is an interrupt pin. So these are the PWM pins as indicated in red. Then there are interrupt pins, which is this one and this one. So when the program is running, if the interrupt gets activated, okay, we have some examples and programs to do that. So if it gets activated, immediately the program will stop. Okay, that is you would have seen that these are also called emergency stops in all machines. All machines have emergency stops. So if you just activate the interrupt, immediately everything stops. Okay, so this is the basic structure of the Arduino pin. So what we can see here is, number one, there is a reset. There is a physical button here. There is a physical button which is a reset pin. So if you press it, whatever is running will get reset immediately. Okay. There is also a LED. So there are lights here. This is a power. Okay. And there is one here. That means the moment you connect it to the PC, this will start glowing, indicating that it has made connection with your PC. Okay. And the PC is giving it the power through the USB connector. Now there is a PWM, there is a LED also here. So there is an LED there, okay, which glows. Okay, so there is an inbuilt LED. So if you want to check some program by blinking the LED, which we'll see, you can use that LED, or you can connect an external LED by connecting it to one of the pins in here. Okay. So this is the basic outlay of the board. If you have a board, if you have purchased a board, or if you have seen a board, then look very closely at these pins and what is doing what. Okay. Now, port pin directionality. The pins can be input or output from Arduino's perspective. So when we are saying input pin, that means you are inputting something into the Arduino board. Okay, so an input pin will mean that you are inputting some information in, for example, a sensor. An output pin will mean you are giving something out, for example, to a motor. Okay, so it is from the Arduino's perspective. Now, input, when you want to take information from the external world, for example, sensors into the machine control unit, these are called input. Output, when you want to change the state of something outside, for example, turn on a motor, provide some voltage. Okay. Now, pin default mode defaults to input direction on power up or reset. So first time when you connect it, all the pins are reset to the input direction. That means they only receive information, they don't give information. Okay. Now your program can change the directionality of a pin at any time. Okay. You can set it as an input or an output pin. And how do we do that? So the syntax or the program, the syntax line is very, very simple. It simply says pin mode, okay, pin number. So that will be my pin number. And this is the mode, input or output. Okay. So it is very, very simple to set. So before you start the experiment, we have to set, or before we run the program, we have to set the pins to input or output. If you're taking a sensor input, it becomes an input pin. If you're driving a motor, it becomes an output pin. Okay. Now, pin mode definition as input or input pull-up. So input, when you say input, it configures the pin as an input. When configured as an input, the pin is a high impedance state. This means it does not drive any current and effectively disconnects the pin from the circuit, allowing it to be influenced by external circuits or components. So which means that any sensory signal which is coming from outside can come in. Whereas if you're putting an input pull-up, configures the pin as an input and activates the internal pull-up register. When configured this way, the pin is internally connected to 5 volts or 3 volts, depending on the board, through a high voltage resistor. This ensures that the pin is in a known state high when it is not actively driven low by an external component. Okay, for example, I talked about an interrupt. Okay, so in this case, it will be maintained as high until it is driven low by an external component. In that case, it understands that there is a change in state. Okay. Now, the basic coding structure, basic coding or the basic program structure looks something like this. It consists of 2 parts. The first part is this one, and the second part is that one. So what you would guess by now is the first thing you attach your board to your PC. Okay, download the IDE, open the IDE, set the board, set the COM ports wherever it is connected. Then you open a program that you want to run. For example, I want to run this program. Let me just come here and look at this. So I want to run this program, which is basically blinking an LED. Okay, so this program essentially blinks an LED. So what it is supposed to do, explain it to you so you understand more clearly. So the top one is going to blink an LED, like in your Diwali lights, you know, it blinks. So we are going to blink an LED. And you can see that the LED is here. So the LED that is blinking is here. Listen see it very carefully. So it's becoming on off, on off, on off, on off. Now the same LED, this is an inbuilt LED that I was talking about, that there is an inbuilt LED there. Now I can also blink the LED by connecting it to the ground and 13 number pin. Okay, suppose I am defining the LED pin as 13 and ground, then I can connect in the second figure here. So this is an external LED, this one, external light. This is connecting to 13, you can see the number there, and it's connected to ground. Okay. Now I can write the program to blink this one also. Okay, this is an external LED. Now if you see this one is blinking, it comes on off, on off, on off, on off. Okay. So this is an external LED. Now in place of this, I could have put something else. Okay. So it will keep blinking like that. Now the program for this looks something like this. Okay. This is the program for the LED blinking. Now this program, before we go any further, has 2 parts. The first part is the input. Okay. Okay, this is the program. The first part defines the global variables and includes the header files here. Okay, so first of all, you have to define which is your pin. Which pin are you talking about? For this LED blinking program, we were connecting the LED to pin number 13. So I will say that this is connected to pin number 13 and pin number 13 is an output pin. Okay, so I have to define which pins I'm going to use, what is the function, and if you're using any header files, that will come in, all information will come here. So the board understands that this is the way it is supposed to act. Then the second part of the program is this part. Now the second part of the program is the program which does what you want it to do. For example, in this case, the LED was blinking. So send voltage or make it high or make it low. High means making some voltage out as high, 5 volts. Setting it low means setting it 0 volts. So how are we blinking? Okay, so in 13 number pin, what I'm doing is I'm making it high, okay, which means it is 5 volts, and then I can make it low, so it means it is 0 volts. So here it is on, here it is off. That's what the program is doing. So I'm telling it that I'm going to use my 13 number pin, and 13 number pin I'm making it high. I'm also connecting it to, so the LED is connected to 13 number pin, okay, and I'm making it high for some time. That means I'm giving it 5 volts. Then I'm making it low, means I'm giving it 0 volts, and I'm continuing to do that. So this is an infinite loop. Okay, now I can also put a timer. Okay, I can put a timer, I can put other loops. Okay, I can put delays. Okay, so I hope you understand the basic structure of the Arduino code. It has two parts. One part tells the board which pin is supposed to do what. The second part is the actual program which is running the task that you wanted to do. Okay, now which means that now apart from this very simple program that I just explained for blinking an LED, you may need to have you may need to take sensory input, you may need to do motor control, all kinds of other things you may need to do. So there are other possibilities also which are allowed. First of all is that you can have a digital read. So the structure of the language, these are structures of the syntax. Digital read pin number. Okay, so it understands that this is a digital read pin. Digital write, pin number and state. What is the meaning of state? State means whether that pin should be low. Low means 0 volts, and whether it should be high, it means basically 5 volts, 3 volts or 5 volts. Okay, so low means 0 volts, high means 5 volts. Okay, so the digital write pin number again, and what is the state of the pin? If I make it high, then that pin is going to give out 5 volts. Okay, then analog read pin. So some sensor is connected to pin number, say some pin number, just for example 10. Okay, so I'm connecting the sensor in there. So it understands that whatever is coming into it's a read pin. Okay, so whatever is coming will be taken as a read. It will be reading. Now analog write pin would basically mean that there's a pin number and it will write in there a particular value. Okay, so in digital write you can see the state is high or low, whereas in analog write this value can be anywhere between 0 to 255. Okay, what is the meaning of this? The meaning is I had an LED. Okay, I had an LED. Okay, now the LED is going to blink. Okay, blink means it is going to glow. Let me use the word glow. Like a bulb, you can imagine there's a bulb. Okay, so this is going to glow. If I give it 5 volts here, 0 to 5 here, it will glow. Now if I give it a lower voltage, suppose I give it 3 volts, it will glow less. If I give it 2 volt, it will glow even less. If I give it 1 volt, it will glow even less if I give it 0.5. So I can control the brightness of the LED. Okay, so I can control the brightness of the LED by controlling this voltage now. Okay, so in digital write, its state is high or state is low. That means it will glow or not glow, okay, with full voltage. Whereas in analog write, I can change this value from 0 to 255, so it will have different, it will glow with different brightness. Okay, I hope you understand that. Okay, now the output pins can provide 40 milliamperes of current, and the writing high on an input installs a 20 kilo ohm pull-up resistor. Okay, so essentially we have a digital write here and we have an analog write here. What is the difference? This one has a high state, low state. This one you can put different values and put different outputs there now. Okay. Now, this is the first program that we looked at today. So let's look at this program again. So the first part is we are defining the pin. So we are defining pin mode 13. This is the pin number, and this is an output pin. That means I'm going to give a voltage out from this pin number. So it understands pin number 13 is an output pin. Then this is the second part of what the task it is doing. Okay, so it's a digital write. It is giving a voltage out. LED, this is built-in LED is connected to 13. It understands that internally, or you can write 13 here. If you make it high, it becomes 5 volts. Then I give a delay of 1000 milliseconds. It waits, it makes it high, gives it 5 volts and waits for 1000 milliseconds. Then digital write LED pin 13. It makes it low, means makes it 0 volt. So basically what it is doing, it is making it high, low, high, low. It gives delay again, and then this goes into an infinite loop. So there is an infinite loop there. Okay, so I hope you understand what this program is, and this is exactly what I showed here. Okay, so we are telling the microcontroller that we are connecting it to pin number 13. You can see there is pin number 13 there. If you see very carefully, it's pin number 13. Okay, so one wire is green, pin number 13, the other is in ground. So it understands that pin number 13 is connected to an LED now. Okay. Then on this pin number 13, I make it high. That means I give 5 volt. So the bulb starts glowing. Then I delay 1000 milliseconds. Then what I do is I do digital write again on pin number 13 and make it low, means 0 volt. So it goes to 5 volt. Okay. Then it goes to 0 volt. Then it goes to 5 volt, goes to 0 volt, 5 volt, 0 volt. It keeps doing that. And there is a delay of 1000 milliseconds in between. And that is how it is blinking. So if you look at the blinking part, okay, you can see there is blinking and there is a delay in between that. That is where it is connected to this. Okay. Okay, so today we looked at the very basics of microcontrollers and how do you program, the very basic fundamentals, how do you connect and how do you proceed. So from the next class again, we'll try and have a little bit of theory and then a little bit of experiments where we'll actually show you how to connect, how to control a motor and how to take sensory input, sensory output, so that towards the end of the course, you'll be able to control actuators, sensors, and make very simple devices. For example, if you're doing temperature control, light on off control, controlling a very simple mobile robot, you'll be able to do that very easily using this microcontroller. This microcontroller is very simple and very cheap, but then it is very, very powerful and you can do many, many applications using that. So we'll stop today. Thank you.